So recording has started. Okay, so we are talking about LFSR based stream cipher. For stream cipher, what we have? We have a key shared between two party, Alice and Bob. They have a same key, and with that key, they have a pseudo-random bit generator. Pseudo-random. Now this is a key stream generator basically, but we want this to be random. I mean truly random, but we cannot get the truly random. We discussed in the last class. So that's why we call this to be pseudo-random number generator. Or you can say a key stream generator, which takes the key, secret key, which is shared between Alice and Bob, and then it will keep on generating the key stream. So this is our key stream. So this is the ith key stream. So once Alice has this key stream, Alice has the M message, which is also this 0-1 bits x1, x2, x-size. So Alice will just do the bitwise XORing to get the y1, y2, yi's. So then Alice will send. So yi basically xi, xor, ki, alpha is only. So this is the encryption, and for decryption, Bob is receiving y1, y2, yi, the ciphertext bits, and Bob has the same key, so Bob can have the same this p pseudo random r number g prng, same prng, same box Bob should have, and once Bob will give the same input as a key, it will give us the same key stream bits. That is the important. We should get the same key stream bit. So then Bob will XOR with this, and Bob will get back the message. That is basically the whole idea of the stream cipher. Now we have started with one such key stream generator or pseudo random number generator, that is LFSR. We started. So yeah, so we have started one such pseudo random number generator, which is LFSR. Just to recap, so LFSR has a 4-bit LFSR. Say 4-bit LFSR has 4-bit register. Each register is a flip-flop which can store a single bit, and in each clocking, which can update its bits by depending on the connection. So you may have connection over here, you may have connection over here, like this. So this is one example of LFSR. So these are the states, internal state. So these are the bits. These are the flip-flops. So this is a 4-bit LFSR. This is nothing but 4-bit register. Okay. So 4 flip-flops basically. They are connected with some nice connection, so that when we clock it, suppose it is initialized by some values. Now when we clock it, it will just take this out, and then so it will just so when you clock it, it will come. This will come here. This will come here. This will come here, and this one will be out. That is our first key stream, and this will be this field. This will be filled by the feedback. That's why it is called linear feedback. Feedback is asking to XOR between these two cells. This is 1 1 1, so this will be 0. Now we copy this here. Now this is our value, internal state value. Okay, so now again we do the same thing in each clocking. We'll perform this shifting by business. So 0 will come here, 1 will come here, so 1 will be out, and this will be these two, because this is our now the value of the internal state. So this is one, like this we have discussed this. So this eventually will give us the key stream. And we have seen that if we, so this LFSR can be connected with, can be associated with a polynomial, depending on the connection. So this LFSR is basically, so one will take, then if we have a connection with, so this is kind of coefficient of x, coefficient of x square, coefficient of x cube, coefficient of x to the power 4. Now if you have a connection, then that will contribute. So we have a connection over here, so 1 x is x. Now there is no connection on this cell, so there is no x square term will come. Similarly, there is no x cube term will come, but we have a connection in here, so we have a x4 term. So this is our px corresponding to this LFSR. So this is a one-to-one correspondence between LFSR and a polynomial. If you have a 4-degree polynomial, then we can have a LFSR. Like for example, if we have given some 1 plus x plus x square plus x to the power 4, sorry, then we can easily think of a corresponding LFSR. So we have x, so we have a connection over here. We have x square also, we have a connection over here. We don't have x cube, so there is no connection. We have x to the power 4. We have a connection over here like this. So this is our LFSR. So this is so we have seen if the LFSR, if this is a primitive polynomial or irreducible, then or not only irreducible, we need primitive also. So primitive, all these things we will discuss when we talk about this mathematical background, some mathematical background. Irreducible primitive polynomial are basically irreducible. Irreducible means which cannot be reduced further. Like for example, if x plus x square plus x cube, this is not a irreducible polynomial because it can reduce. We can take x common, 1 plus x square. So this can further reduce. So this is not a irreducible polynomial. So primitive polynomials are irreducible polynomials, but not only that, it is a generator of certain groups. So I will discuss those in some form later stage. So if we choose this to be primitive polynomial, then we have seen by one example that this will give us a full period. Full period means if this is 4-bit, we should be able to get full period of 15. So our key stream is 15. So we can easily encrypt 15-bit messages. Okay, so this part is we have already covered. Now we'll see how good this stream cipher is. Any questions so far? Okay, if not, then we can proceed. Okay, so now we want to discuss how good this stream cipher is in terms of the attacker point of view. So this is called cryptanalysis of LFSR based stream cipher. Stream cipher. So cryptanalysis will be done by Oscar, the bad guy. Okay, so again I have to write the same picture, Alice, Bob, and they have this public channel which is captured by this Oscar. Now suppose they are using LFSR, the 4-bit LFSR for their, and that is public. So both all the people is having this. Even Oscar is also having this connection. Maybe here. We have to fix that LFSR before they use. So they cannot change in material. I mean, so we fix the encryption algorithm. Here encryption algorithm is basically the XORing with the key stream bit. So this key stream bit generated is the part of the encryption algorithm and decryption algorithm. So we fix it, and then we have, and then that we assume to be public. So everybody is knowing this. So Oscar is also knowing their LFSR. Bob is also having the same LFSR. Bob has to decrypt it. Okay. Now they have a key. Say key is say alpha 1, alpha 2, or use some other key. Say beta 1, 4 bits a key, beta 2, beta 3, beta 4. They have same key. Beta 4. Okay. Good. So now Alice is having a key string which Alice wants to encrypt. So Alice will generate what? Alice will generate this alpha 1, alpha 2, alpha s1, so forth. So then Alice will do what? Alice will generate y1. Y1 is basically x1 XOR alpha 1, y2 XOR alpha 2 kind of thing. So can anyone tell me what is alpha 1, alpha 2, alpha 3, alpha 4? Are you there? Let me check. Am I there? Hello?
Yes, sir.
Oh, thank you. Actually, this is very, I can't see you. That is the problem. So some yes, no will fine. Yeah, so can you tell me what is this alphas in terms of betas? What is the alpha one? So if you, so this is our LFSR, right? So this is our LFSR.
The alpha 1 is beta 4.
Yeah, so depending on how, which way we are loading. So if you are loading this, say beta 1, just to, doesn't matter, beta 1, beta 2, beta 3, beta 4, like this. And if you are generating this, so you said alpha 1 is? Alpha 1 will be just, we
In
are,
this case, it will beta 1.
yeah, so we get beta 1. And what is alpha 2? Alpha 2 is the next key string. How we get alpha 2? Any guess? So just do this. So this beta 4 will come here, beta 3 will come here,
Beta
beta
2.
2 will come, beta 2, yeah, and this will be combination of, I mean the XOR with alpha 1, beta 1 and beta 4, right? Now what about beta alpha 3?
Beta 3.
Beta 3, thank you. Alpha 4,
Beta
beta
4.
4. Now tell me alpha 5. That is more interesting.
Beta 1 plus beta 4, XOR beta 4.
Beta 1 XOR with beta 4.
It's
Now
not
alpha
beta.
6. Alpha 6. Just
Beta
one.
1 XOR beta 2 XOR beta 2.
Beta 1 XOR
XOR beta 4
beta 4 XOR
XOR beta 2.
beta 2. Thank you. So basically, can you observe this? Any alpha it can be written as this linear combination of this beta. Some D1, D is either 0 or 1. Beta 1 XOR D2 beta 2 XOR D3 beta 3 XOR D4 beta 4. So DIs are basically 0 or 1. Is it okay? So they are basically linear. Any alpha, alpha, is this okay? Now suppose, now we talk about some attack, Oscar. Suppose Oscar knows, is this is okay na? Some DIs. You see here alpha 1 is just there, all the DIs are either 0 or 1 here. So we have all linear combinations over here. So they are basically the linearly related with this secret keys. So beta is basically the secret keys. Now can you think of an attack from here? So that means alpha 2021 is also a linear combination of some combination of say beta 1, maybe beta 2, or maybe beta 4, something like that. Okay. So any alpha 50/50, like that. Okay, so can you mount an attack on this if we have this thing? We know this. We know these alphas are nothing but a linear combination of these betas. So that is somewhat dangerous in terms of in terms of the attack point of view. So what attack this adversary can mount? Oscar can mount. Any guess?
The chosen plain text attack.
Why chosen? Why not known plain text attack? Suppose
Yes,
Oscar
sir.
has some plain text and ciphertext. Say Oscar has say X 2021 and Y 2021. This is the plain text bit. This is the cipher. Then that means what? What Oscar has? Alpha 2021, right? Because you see, this is basically XOR with the alphas. So if we have these two, then we can XOR. So basically, Y 2021 is nothing but X 2021 XOR with alpha 2021. So if we know these two, then this is nothing but XORing between these two. So this is basically non-plain text attack. So if we have some plain text, non-plain text and corresponding ciphertext, then basically we are having some alphas. So if we have some alphas, then what type of attack we can? Then we have some linear equations. Is it not? If we have alpha 2021, we know this is some linear combination of say the DIs are known basically D1 beta 1 XOR with D2 beta 2 XOR with D3 beta 3 XOR with D4 beta 4 prime you can say. I mean, now if we have say alpha 30,000 something like that, we have D1 prime beta 1 XOR with D2 prime beta 2 XOR with D3. This D1 D2 they are known coefficient, right? They are either 0 or 1. Dot 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 dot. So we have some equations, and this is a linear equations. So we can solve it. So that is called algebraic attack. So that is the linearity is somewhat dangerous over here. You understand this? So this linearity is somewhat dangerous over here. So we can just have a because this is very simple operation. It's a linear combination. Linearly we are doing that business over here. So we want to destroy this linearity so that we cannot. I mean, the adversary cannot think of this type of linear attack. Okay. Is this okay? Before we move to the solution to prevent this type of attack. Any question? You got it, na? If we have some pairs, then we have some alphas. So if you have some alphas, maybe for this example, 4 bit, we just need to have 4 alphas maybe, because then 4 equation, 4 unknowns, then we can solve it. Anyway, but if you have, our life is not so simple. We have bigger size LFSR, then we can apply some Gauss elimination method or something like that. So there are some optimization technique also somebody can use for solving the linear equations.
So
Good.
how Oscar will know the values of DIs?
DIs are because Oscar knows the alphas. So alphas must be some linear combination of these betas. Oscar knows this X and Y, na? So that means Oscar knows this alpha 2021, and that
Yes,
is
sir, but
nothing
he
but
have to
the
calculate
linear.
the beta is, I think. So for that he
But
needs.
that is in some form of the beta is linear combinations.
Yes, sir.
So from there we get some linear equations.
Yes, sir, but for that he should know the value of DIs, like D1 does, D2 does.
DIs are basically we know this has to be some linear combinations of betas.
Okay.
So basically we will get some equations. So from there we can guess, na?
Okay, sir.
Just think about it.
Sir,
Yes, please.
sir, is the polynomial available for the Oscar?
Yeah, because if Oscar knows the LFSR, then polynomial has to be known.
Yes, sir. Thank you.
So now to prevent this, we have to somehow bring the nonlinearity there. So for that we will use what is called Boolean functions. So suppose we'll just make little more LFSRs over here. We'll use, instead of one LFSR, suppose we use the two LFSR, or say for example 4 LFSRs. So we have 4 LFSRs here. Every LFSR is 4 bits here. Okay. And now each is having some connection. Maybe this is this connection. Maybe this is different LFSR. This connection. Anyway, somehow we have 4 LFSR. This is L1. This is L2. This is L3. This is L4. We have 4 different LFSR. And then we take this over a nonlinear function f, which takes this output of the LFSR. So this is some we'll not use x1. So this is z1, z2, z3, z4. Even we can have 2 also, doesn't matter. So then if this is a function which takes this f of z1, z2, z3, z4, and we want this to be nonlinear function. We not just simple XOR with this. So nonlinear means we can just take x1, z1, z2, then XOR with z1, z2, z3, like this. Okay, z2, z4, like this. So any nonlinear. So these are called. I'll explain that. So then this is f of z1, z2, z3, z4. Then we have, this is 1 bit. So this is our alphas. This is our alphas. This is our key string. This is our key string. So every time what we do, we have a Alice is having a secret key. Say that is 4 bit. So what Alice will do there? Alice will put that in this. Suppose Alice is having 4 bit key, which is shared between Alice and Bob. So Bob is also having same key. So what Alice will do? Alice will put this as a what is called internal initial state of this LFSR. All has to be filled. So we'll use the same values for all LFSR. That is the strategy we are using. So now suppose we are now clocking. So every time it is outputting some Z-dice, Z1, Z2, Z3, Z4, and then we apply this function. So this function will give us a alpha. So first clock it will give alpha 1, then alpha 2, alpha I, like this. Okay. So now so this is our key string generator. So whole thing. So it is we are using underline LFSR, but we are making this to be key stream to be nonlinear. This key stream generator is a nonlinearity we are introducing by introducing this f function. F is a Boolean function. What is Boolean function? Boolean f is what is the, so f is taking some input. So z1, z2, z3, z4. Sometimes Boolean function is written in tabular form. So we have all possible combinations 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. How many are there? We have many, no? Anyway, 0, 1, 0, 1, like this. How many are there?
Sir, 16.
16.
To the power
Yeah,
14.
Yeah, 2 to the power 4 basically. So now Z has some values, we can have some values. So So maybe this 0, 0 is going to 0. This is maybe 1, 0, 1, like this. So this is a whole area of some area. I mean, this is you. Some of you must be familiar with this Boolean function. We can. This is a tabular form, and we can have a algebraic form of this. So f of z1, z2, z3, z4. This may be in algebraic. There are some normal form also there. So depending on where is x, we can get this expression. So those things I am not covering in this course, but that is another area. I mean, good area. I mean, people, this is little old area, but this is a very nice area. I mean, if one of you can go for the project in this area, if you are interested in this discrete mathematics, like there you will see how we can construct a good function. Good function means balance function. Balance function means we just count the number of zeros, number of ones in the output, and if they are same, then it is called balanced. And then also there are some technique to measure the nonlinearity of this function. So those things are there. So this is called Boolean function. Boolean function, and this is a whole branch of area which you can just focus on. But for our crypto syllabus, we'll just mention this one. I mean, we'll not go further on this. Maybe if time permits, we'll see some nonlinearity of this, but this is the thing. Okay, so this function is given. It is a part of the keystream generator. So once we have this function, then we can Alice and Bob can use this after getting the output Z1, Z2, Zn from this. So basically we have this 4-bit LFSR, and we have a function over here, f function. It is giving us the keystream. So this whole process is our keystream generator or pseudo-random number generator. Is this clear? The way we are, so it will give the key, secret key, which we are, it will generate as the, and this same thing has to be there with Bob, and the same thing is there with the Oscar also, because this everything is public. This connections, these LFSRs, this F function, all are public. Only secret is this key. So key is not known to Oscar, and here this is not a linear function, so we can just avoid this linear attack like algebraic attack. Okay. Okay. Any question? Before we move to the general structure of a stream cipher. So this is the LFSR is very nice because advantage of LFSR is very fast. Why we use LFSR? I mean, it's very fast. Why it is fast? Fast in what sense? Both in hardware. If we have a chip, we just need a connection of that XOR bit. We just need the XOR bit, hardware, and both in software. Software also it is very fast. So LFSR is fantastic when you implement it. Ultimately, we have to use the cipher. No, ultimately we have to use the encryption and decryption functions, algorithms, for us to encrypt our messages. Good. So that's why we don't give up LFSR. We just, although it is linear, but we wanted to make it non-linear using the Boolean function with the help of Boolean function. So there we can use a good Boolean function in the sense that with high non-linearity, it is a balanced. So all these things are there. Okay. So this is one area you can explore. Can you move to the some modern stream cipher? Any question, please? If you ask
No,
question,
sir.
then I'll feel you are there. General structure of a stream cipher. Good. No question means you are getting or you are sleeping. Anyway, I cannot understand both the thing because you are at home. but I hope you are getting. Okay, so general structure of a stream cipher. So okay, so basically we have a kind of finite state machine. ST. For you can relate this as a with a LFSR. We have a LFSR. LFSR is a we have some state and internal state. Here we use 4-bit LFSR, so we have 4-bit 4-bit. But here in this example, when we talk about this combinations, let me bring. So here, what is our state size? Our state size is not 4-bit. We have how many bits? 16 bits. So even if Alice and Bob have 16-bit key, then also we can fit it. Like say, if we have say beta 1, beta 2, beta 16, what we do? We put this beta 1, beta 2, beta 3, beta 4 in the first LFSR and say that this is the strategy what we will use. Beta 5, beta 6 to the second, and that is also fine, na? Any problem with that? So if we have our 16 bits, because each we are using 4 LFSR, each LFSR is 4 bits, so you can easily use the 16 bits. So that is the way. So we can just fill it up, then we can run the show. We can so same thing Bob will do, and Bob will get back this message anyway. So that is the strategic thing, or we can use the same initial internal state for each LFSR. So let me just go to the general structure. Okay, we have basically a finite state machine. Finite state machine. Why finite? Our computer cannot understand infinite, so we have to have you can say it is a register. We have finite computer. Most of the current computer is 64-bit register, so it is a finite state machine with 64 bits. So anyway, we have some size of this machine, so it is a finite state machine. Okay, and which is having some states. State sizes depending on our designer. So we have some state, and this state will update with some function g. So g will take the every time g will take the internal state, and it will do some. For example, for LFSR, it is just doing some XORing with some of the cells, some of the states. Very simple operation. But our life is not so simple always. So there are some modern stream cipher where we will use some other operations, like we can use the multiplication also. We can use the shifting. I mean the modular operation. So something like that. So there are a hell lot of stream cipher available. So, but anyway, I'm giving you the general structure. So it will give us ST plus 1 next state. So we just update this g is called state update function. State update function, which takes the value of the internal state of this machine, and then it will give us the value of the next state. Value of the next state. Okay, like for LFSR, we are doing the XORing of some of the cell, and we are changing this value. So the other values are just shifting of the previous values, but the last value is changed by this feedback. So, but anyway, total every value is changing. So that is done by the state update function g. And then how to get the key stream? Key stream, we get another function h, which take the state, the current state, value of the current state, and it will give us the alpha t. It will give us the key string. So basically it will generate the alpha 1, alpha 2 like this, alpha is 1. Okay. So this is a sort of general. So this is asynchronous stream cipher. Here we are not mixing the plain text. But there are some modern stream cipher where we mix the plaintext. But anyway, let us just first understand this a simple machine. Is it okay? So we have a, so just relate this with a LFSR. For example, we have say LFSR which is having a finite machine which is having some states. So that state will update by using some G. So for LFSR our G function is that XORing business with the shifting part, and it is taking the current state and it is giving us the next state. So T is the time. So we initialize by S0. S0 is the internal initial internal internal state value S0, and we have some then G S1. How will get S1? S1 will be G of S0 kind of thing. S2 will be G of S2. So this state is updating every time with each. So how much this required? We key required. We'll do that. And this H is the keystream generator function. So H is the, I mean, whole thing is the keystream generator part, but H is taking the internal state. So say first internal state is S0. So if we apply H on this, H of S0, it is giving us alpha 1. Then the next state is S1. So H of S1 is giving us the alpha 2, like this keystream. Okay. Any question on this? This is the general structure, but you can always relate this with our good friend LFSR. So this having some issues like some attacks was mounted because of this key size. If the key size is less, then we can always think for some exhaustive search or time memory data, some generic attack. So those we'll discuss when we talk about details on the cryptanalysis. But that is the problem with this type of finite state machine. If the state size is less, if we are using say 32-bit register, then it may we can mount some attack like generic attack. And because if we just directly put the our key shared between Alice and Bob, if that is 32-bit, then we can directly put as a internal initial state. Then we can do the we can just think of some attack on this. To avoid that, the key, even the key is less size, because key, if we increase key, then it will another botheration is there. So to avoid that, we introduce what is called IV in the system, or initialization vector IV. So what is IV? It is a public thing. So it is a part of the initial process. So we have a state. We have a finite state machine. We have a finite state machine which is getting updated by a G function, and which is having another function H, which is giving us the keystream. Okay. Now this is a finite state machine. Okay, it has some states, and that state has to be initialized. So internal, this is very important, internal initial state. So we want to know what is the internal initial state. So far, what was our internal initial state? For example, LFSR. We are just putting the key shared between Alice and Bob, the K, that we are using here as a internal initial state, that is S0. S0 our internal, this is our S0. S0 is the internal initial state. But we won't do that. We'll have an initialization process over there. And then after this internal initial state, we'll start generating the keystream straight away. But here, most of the modern stream shaper, what they do, they don't, just do this internal initial state, initial running some times before generating the keystream. So they what they do, they use some IV and the key. With this combination, they put it here as a S0, but that S0 they are not telling internal initial state. So they are putting here and they run the show. They run this update function. Sometimes maybe for some stream Cipher it is 100 times. They don't start generating the key stream. So after 100 times, it will give us some state, say S100. So that is our we start. That is our we say our internal initial state, and after that we start generating the key stream. And that is required to avoid some generic attack. We'll come to that. But that is the idea of introducing the IV or initialization vector. So we just because key size is less, so just try that. That's the reason we put another IV which will fit there, and this IV and key will together fit in there, and we run this. We update this state by this state update function. Forget about key generation now. We just update. We ignore this part. Update, and after certain time we are happy. Okay, we mix this very nicely. Then we start generating the after this, say 100 times, or some stream Cipher they use for, they wait for say more than 200 times. Okay, so after that they start generating the history. Is this okay? Is this clear, this idea of introducing IV and that initialization process? So in the earlier we didn't care about the initialization process. Straight away we put the key as a S0 in the LFSR based case, and then we start generating the key stream. But here in the modern stream Cipher, what we do? We wait. We not we wait for some update. So we store this IV and the key into this state, finite state machine, and we'll start updating this. So that part is called initialization process, initialization or IP, initialization process. So there we keep on updating, and then after some time we are happy. Okay, we have done enough update. Then after that onwards we start generating the key stream. That is the idea. Okay, good. And this is the encryption, and similarly Bob will do the decryption. And also in the modern stream Cipher we don't do this bitwise. We have a bulk of key stream. I mean, not a single bit, maybe we have a bulk of key stream. So I suggest you to look at some modern stream Cipher like Snow, Helix, Rabbit. These are the name of the stream Cipher. We will not cover this in our class. I just gave you the general structure. So I suggest you to look at this, and later on we may give some assignment on the implementation assignment on this to implement this. Okay, so I think this is the stream Cipher we wanted to cover, and the next class we will do the, again we go back to the block Cipher. Then we discuss this how we can encrypt a bulk message, like more than, so block Cipher is having a fixed size. So but if we are messages more than that, suppose we are using DES is 64-bit block Cipher, but suppose we are encrypting a more than 64-bit message, so we have to break it into blocks. So the way we did in the previously, but that has a problem. So we'll discuss that. That comes under the topic called Morse-of operations. How we'll do that encryption. So I think stop here now. Any question before we stop? Gain is also on another. These are all modern stream Cipher. Are you there? Can you hear me?
Yes,
Yes,
sir.
sir.
Any question? Or it's okay? So let me stop the recording. Yeah, any question?